Welcome back to ENE 480 Environmental Measurements Laboratory. Again, we will continue with our discussion of statistical analysis for environmental data, and this is part 2 of that discussion. We left off discussing confidence intervals. In this unit, we will expand on that discussion by looking at how we can compare two sets of data to determine if the differences in the averages of these two sets of data or observations are statistically significant at a given confidence interval. As mentioned in the first lecture, we'll focus our discussion on normal or Gaussian distributions. Okay, let's start by looking at several sets of graph data. And if we look at the graph on the left, we have two means. So one about maybe 57, and then the other maybe 49, 49.5, somewhere in that range. We also want to look at these error bars. And what we see is that there are no overlap in the error bars. So just looking at the data, we could make the reasonable conclusion that the averages of these two observations are significantly different. So we've got no overlap, so we can make this conclusion. Now, if we look at the graph in the center, what we see is that there is significant overlap. So there, we probably can make a reasonable assumption that the averages are not significantly different. And then in this third graph on the right, there is some overlap, so it's really hard to tell. Well, this is when our statistical tests become very useful, and then we can determine statistically if there is a significant difference in the averages of these two data sets. We'll use the student t-test to determine if the differences are statistically significant. So the test assumes that the data are normally distributed. Next, we need to formulate the null hypothesis. So the null hypothesis that we'll formulate is that the means are equal. And then our alternate hypothesis is that they're not equal. So typically, because of this assumption, because the way that we formulated these hypotheses, when we do the test, you'll see that we'll use the two-tailed t-test. Now, if the calculated t is larger than the number that we obtain from the table, or the critical value, then we will reject the null hypothesis and conclude that the differences in the averages are significantly different. So in order to determine if the two averages are different, we need to answer a few questions. Are the averages dependent? So if the same samples are used to obtain these observations, then yes, the averages are dependent. Are the averages independent? So did we collect separate samples? Are these separate observations? If that is the case, then the averages are independent. And then we need to determine if the variances are known or if they're unknown, and then if they're unknown, are they equal or are they unequal? So let's say we have two sets of data. These can be from two different samples. These can be from two different groups. These could be from the same location on different days. There's a number of scenarios that we could think of in looking at these observations. And what we want to know is, are the averages truly different? Now remember, we never know the real true average of this population. We only know the parameter. Okay, we only know what we can measure. which is a subset really of that true population. So what we will do is we'll determine if the tails of the two distributions of these means overlap enough to say that the averages are the same or different. And we do this by a modified pooling of the two variances. The first case we'll consider is where we have two independent averages with known variances. Often we don't know the variances, but in this case, let's say we have a well-established method that provides a known variance along with the methodology. So we can use that as our known variance. Now these are independent averages, so they're taken from two different sets, two samples, for instance, taken from two different groups, two samples taken from two locations, and we're looking at, can we determine if those averages are statistically different? What we'll do is, again, we'll use the student t-test, giving you the equation here. Typically, we'll use the absolute value of the difference in the means of observation set 1 and observation set 2. Because the variances are known, we will assume that the number of degrees of freedom are infinite. So let's look at an example. Send out a group of 480 students, and they go and they take 3 samples at one water fountain and 5 at another. And they're measuring these samples for the free chlorine residual. And the group members wish to know if the means of the free chlorines at the two different locations differ significantly. The instructions for the free chlorine residual test state that the method has a standard deviation of 0.025. So we have a known standard deviation. So the data that they've obtained is provided here in this table. The equation for the t-value that we'll calculate is given here, and again, as I remind you, that in this case, the number of degrees of freedom are infinite. So we'll obtain a student t-test. Typically throughout the course, as I've mentioned in the first lecture, we'll use a 95% confidence interval, so that is a alpha value of 0.05. This is a two-tailed t-test table. We have a null hypothesis that the means are equal, an alternate hypothesis that they're not, so that's why we'll use this two-tailed t-test. And if we look at the table, we have an infinite degrees freedom, we have a alpha value of 0.05, so in this case we have a t-value of 1.96. So again, looking at the data here, what we want to do is we want to calculate the means. So we've calculated the means for both sets of data, and at location A we have 3 observations, location 2 or B we have 5 observations. The next thing we'll do is, again, we've got our null hypothesis and our alternate hypothesis. We're looking at the 95% confidence interval, so alpha is equal to 0.05. We now substitute in the values that we just calculated for the means. This is our known standard deviation here, the number of observations, and we calculate t is equal to 1.425. And if we looked at this graphically, what we see here, okay, here is our experimental t at 1.25. Here is our calculated t, the t from the t table. Our critical t is 1.96. And we see that our experimental value is less than the critical value. So because that is the case, we can now conclude that there is no evidence of a significant difference in the means between the two samples at a 95% confidence interval. The second case we will consider is where we have two independent averages but unknown and equal variances. Most likely, we do not know the variances associated with the two averages of interest, and the variances must be calculated from the same data that was used to determine the averages. So as with before, we'll have the same null and alternative hypotheses. So the null hypothesis is that the averages are equal. The alternative hypothesis is that the averages of these two are not equal. And again, we'll use the 95% confidence interval or an alpha value of 0.05. The two variances are first subjected to the f-test. Note, S1 and S2 are the standard deviations of the two data sets or sets of observations. If the variances appear to be homogeneous, that is that they're not significantly different, then we'll proceed to the t-test. Note here, P is the pooled standard deviations S1 and S2 for the two sets of data. So in this case, what we've done is we used the f-test. If the f-test, if we can show that we have equal variances, then we'll proceed to the student t-test. We'll pool the two standard deviations for set 1 and set 2. And then if the calculated t-value is less than the critical t-value, then we can accept the null hypothesis, and we can conclude that there's no significant difference at the specified confidence interval, which in our case would be 95%. Let's look at a second example. In this case, the variance of the analytical method is unknown. So Group A takes 3 samples from each of 2 water fountains in Fee Hall, where they're looking to measure sulfate. The analysis are done by the same method. The group members wish to know if the means at the 2 locations differ significantly. And as I mentioned, the variance of the analytical method is unknown. So they record their data. They presented here. They've calculated the mean and the standard deviation. The null hypothesis in this case is that the variances of the 2 sets of data are equal, and the alternative hypothesis is that they're unequal. Again, we will look at the 95% confidence interval, so we'll set alpha equal to 0.05. So the first thing we need to do is to use the f-test to compare the variances. So the f-value, the experimental f-value, is equal to the square of the standard deviations. The square of the standard deviation of the first set of data divided by the square of the second set, the standard deviation of the second set of data. And if we substitute in the values for the standard deviations, then we obtain a experimental F value of 9.75. Next step we need to do is we need to determine the critical F value. So the critical F value is given here. Note, we set a alpha at 0.05, but with the F test, we need to use alpha divided by 2. So we'll use 0.025. Again, remember, our alternative hypothesis is that the variances are unequal. So it's really a two-tailed test that we're using. The degrees of freedom in both cases are 2. Both cases we had 3 observations, and the number of degrees of freedom are n minus 1. So we see here that we have a critical F value of 39. As mentioned, we've got a critical F value of 39. We've got an experimental F value of 9.75. Since the experimental F value is less than the critical F value, then we cannot reject the null hypothesis, and then we conclude that there's no evidence of a significant difference in the variances, and now we can pool the data for the variances. So essentially what we're concluding here is that we have equal variances. So our next step is to use the student t-test. So now we're evaluating the means. So our null hypothesis is that the mean of data set A is equal to the mean of data set B, and our alternative is that they're unequal. So again, we're going to use a two-tailed t-test, and our probability, or we're determining, we're testing at a 95% confidence interval, so again, alpha is equal to 0.05. So in this case, we will use this equation here for calculating t. We have calculated our means. The number of degrees of freedom is equal to n1 plus n2 minus 2. So that's 3 plus 3 minus 2, or 4. And the equation for the pooled standard deviation is given here. So again, looking at the same problem, we can calculate, we just substitute into the equation for our pooled standard deviation, and we determined that the standard deviation is equal to 0.46, roughly 0.464. We then use that pooled standard deviation here to determine the experimental t-value. And when we do, we determine that the experimental t-value is equal to 1.056. Again, we will use a two-tailed student t-test. So we said that we had 4 degrees of freedom, okay, calculated from this equation here. And we're looking at the 95% confidence interval, so we have a critical t-value of roughly 2.78. We'll compare that to the experimental t-value that we just calculated of 1.06. Compare that to the critical value. We see that our experimental t-value is less than the critical t-value. So again, we cannot reject the null hypothesis, and we conclude that there is no significant difference in the averages at the 95% confidence interval. Okay. Notice we're not concluding that they're equal, we're concluding that there's no significant difference in the averages at the 95% confidence interval. We can do the same calculations in Excel. If you've not done so, make sure you install the data analysis tool. You'll need that throughout the semester to analyze your data. Now you'll select the data that you wish to analyze, and in this case you will choose the F-test to sample for variances. Be sure to set the alpha value at 0.025 for a two-tail test if you're looking at the 95% confidence interval. Remember, again, what we're doing is we're testing a null hypothesis that the variances of the two sets of data are equal and an alternative that they are unequal. Once you run the F-test, what you will obtain are both the experimental F-value, same what we obtained before at 9.75, and the critical, and it'll say one-tail test. It is the way it calculates it, it is for a one-tail, but because we set the alpha equal to 0.025, the result that we obtain is really equivalent to that for a two-tail test. So again, we see that the experimental F-value is less than the critical F-value, so we cannot reject the null hypothesis, and again, we conclude that there is no evidence of a significant difference in the variances, and we can pull the data. So again, we have shown that we can proceed assuming we have equal variances. We continue, same method, we've got the same set of data. Now again, what we wish to do is do the student t-test. Our null hypothesis is that our means are equal. The alternative is that they're unequal. What we will do in this case is we will do a t-test to sample assuming equal variances. We set the alpha equal to 0.05 in this case. So this really is doing a two-tail test. Okay. The important parameters that you will obtain from this are provided in red. That is your t experimental and your two-tail t critical. So because we said that our means are unequal as the alternative hypothesis, that's why we're using a two-tailed test. So again, we have shown that the experimental t-value is less than the critical t-value, so we cannot reject the null hypothesis, and we conclude that there is no significant difference in the averages at the 95% confidence interval. The third case that we'll consider is one where we have unknown but unequal variances. Approach is essentially the same as case 2. So you're still going to have to go through and do the F-test because you don't know what the variances are. So you'll have to show whether they're equal or unequal. If the conclusion that you make from the F-test is that they're unequal, then you use these two equations rather than the previous two equations. Notice a much more complicated set of equations for your degrees of freedom. So in this case, Group A is really illustrious. They go out and they take 10 samples at each of 2 water fountains in Fee Hall, and they are measuring chloride. They don't know the variance of their method, and they wish to know are the averages statistically, or the differences in the averages statistically significant at a 95% confidence interval? So again, they will calculate the mean, they will calculate the standard deviation, they calculate n, and they then calculate the experimental or calculated F value, and that is 4.77. So I stated it again, just to reiterate, okay, the null hypothesis is that the variances are equal. The alternative is that it's unequal. Again, we're using a 95% confidence interval. So again, we go to a table of critical F values. So we have an alpha of 0.05. We have 10 observations for both sets of data. Again, we use alpha divided by 2. So we will use a p-value of 0.025. We have 9 degrees of freedom in the numerator, 9 degrees of freedom in the denominator, and that gives us a critical F value of 4.03. So our calculated F value is 4.77. Our critical value is 4.03. We see that our calculated value is greater than the critical value, which means we reject the null hypothesis and we conclude that there is a significant difference in the variances at a 95% confidence interval. So now we'll proceed as if we have unequal variances. Again, we can do the same test in using Excel. And as you see here, we get that same experimental F value that we just calculated. We get the same critical F value. Again, we make the same conclusion. Just be careful. If you use Excel, you need to set your alpha as 0.05 divided by 2. So divide, if you want a 95% confidence interval, it's 0.05 divided by 2 is what you'll set the alpha value for in Excel. So I gave you the equations before for unknown and unequal variances. We then substitute our values into that. We have a t value now of 2.5. That's our calculated or experimental t. We have calculate the degrees of freedom. Notice here our degrees of freedom are actually 13.4. You must have an integer value for your degrees of freedom. You'll round to the nearest whole number. So we have 13 degrees of freedom. So again, we will use a two-tailed t-test, I apologize. So we've calculated, here we have 13 degrees of freedom. We're using an alpha value of 0.05 or a 95% confidence interval. So we have a t-value of 2.16. We calculated a experimental t-value of 2.5. Since that 2.5 is greater, our experimental t-value is greater than the critical t-value, we reject the null hypothesis and we conclude that there is a difference in the averages at a 95% confidence interval. So we can say that that difference is statistically significant. And we can show this graphically again. So here is our critical t-value, and here is our experimental t-value. So you can see it is greater than the critical t-value, and we reject the null hypothesis. As shown before, we can use Excel. In this case, we will do a t-test. We will sample, assuming unequal variances. Set your alpha equal to 0.05. We have 13 degrees of freedom. It actually calculates that for you. And you can see that the t experimental is about 2.5. And the t critical is 2.16. It's exactly the same that we calculated before. Again, you see that your experimental t-value is greater than the critical value. And again, we can make that same conclusion. We reject the null hypothesis, and we conclude that the difference in the averages is statistically significant at a 95% confidence level. The last case that we will consider is where the averages are dependent. So here the averages are based on the same sample or samples. So for instance, we have two analysts. They use the same method to determine the nitrate level in triplicate and the same sample. So two students go out. For instance, they're using the same nitrate method, and they're determining the nitrate on the same sample. Or we have one sample, and it's analyzed for nitrate in triplicate by two different methods, same analyst. So we're only changing one factor in this case. Okay, so in the first case, we have two analysts. In the second case, we have two methods. It gets more complicated if we are doing more than that. So in this case, what we will do is we will pair the data. So what we need is we need the same number of observations of both sets of data. Okay, so we can't use this test if we don't have the same number of observations. D is the difference between each set of paired data. S sub D is the standard deviation of the differences between the paired observations. And D bar is the average difference in the paired values. All the other terms we've defined before. So in this case, we have group A goes out. They take one sample at a water fountain in Fee Hall for chloride, and the two students analyze the sample by the same method. They do 10 replicates on that same sample, and they wish to know if the two means differ significantly. The variance is unknown for this method. So the null hypothesis that we're testing is that the means are equal. The alternative is that the means are unequal. Again, we will use a alpha value of 0.05. We're looking at the 95% confidence interval. So I've tabulated the data here. I have calculated the mean, the standard deviation, and we have 10 observations. Done the same for student B. Then I've got a paired data. The average difference, so I've calculated the difference between the paired data. I've calculated the average difference, and I've calculated the sum of the differences. And then I've calculated D squared, and I've summed the d squared. Okay, so I have that value there. I then use the equation for S sub d. I then calculate S sub d is 0.319. My degrees of freedom, 10 minus 1. I then calculate t. So I have a t value of 3.17. That's my calculated or experimental t value. I then go to a two-tailed t-test table. Again, I'm looking at the 95% confidence interval. I have 9 degrees of freedom. So I determine a critical t-value of 2.262. And we can, again, we've got same null and alternative hypotheses. We've calculated our critical t is 2.262. We can show the experimental t value on the plot here, and it's about 3.17. The critical t value, so experimental t value is 3.17. Critical t value, we just calculated here at 2.26. We see that the experimental t value is greater than the critical t value. So we reject the null hypothesis and we conclude that there is the difference in the averages is statistically significant at 95% confidence interval. As with the other methods, we can use Excel. In this case, you will use a paired two-sample for means. Notice it calculates the means for you. Here, when you set up the problem, you hypothesize that the mean difference is 0. Remember, we said that our null hypothesis is that the means are equal, or our alternative hypothesis is that they're unequal. So here, set that as equal to 0. We will determine the experimental t using Excel and the critical t value, and we will make the exact same conclusion. We reject the null hypothesis and we conclude that there is a statistically significant difference in the averages at a 95% confidence level. So based on this lecture, you should be able to analyze the data that you collect throughout the semester to determine if the differences in the averages of two data sets are statistically significant at a given confidence level. So hopefully this is helpful, and you will be able to, as I mentioned, you will be using this throughout the semester.